everything all the new things that I mentioned today is joint work with Manik Dhar, who's a graduate student at Princeton, and Zeev Dvir. So first let me define the object that I'm going to talk about. We say that a set S in a vector space of a finite field with two elements is Km Furstenberg if and only if for every K flat, so K flat is an affine k-dimensional space or a shift of a k-dimensional linear space, V, there exists some vector U such that the intersection of the shift of V by U with a set S is at least M points. So this is a kind of complicated statement, and what I'm going to do is I'm going to track through several different special cases that have been investigated in the past, talk about how those were proved, why there was a barrier to solving this problem, and what our contribution is. And the problem here is to say how small can a Furstenberg set be. Certainly, if you take all of the points, then every k-dimensional flat intersects a set in q to the k points. So as long as m is less than q to the k, it is in fact the set of all points is a km Furstenberg set. So the question is really how small can it be? So let's define this function k of n, q, k, and m. So those are the parameters. It's just the minimum size of a set having these properties. This is the earliest studied special case, and probably still the most famous, is the finite field Kakeya sets. So a Kakeya set is what you get when you say k is equal to 1 and m is equal to q. In other words, the set contains a line in every direction. Take any line, there's some translated line that intersects the set in q points, so it's in fact contained in the set. And this was, I'm not going to go too deeply into the background or the history of the problem, but this definition, and also the question of how small can a Kakeya set be, was introduced by Thomas Wolff in 1999. And he was interested in it as an analog to a very deep and important question in Euclidean geometry. A very similar idea came up independently in work of Lund, Reingold, Vadhung, Wigderson. I think 2003. These guys were interested in randomness mergers and certain ideas from pseudo-randomness. So they're really computer scientists, and the same basic idea came up in the analyzing a construction of randomness mergers, which, again, I'm not going to tell you what that is. It's just there was interest in this problem coming from two different communities. A lot of people were were pretty focused on it, but it turned out to be a fairly easy problem. In fact, I'll give you, let me first tell you what the known bounds are, and then I'll sketch a proof of the lower bound, and we'll see how far can that proof generalize. So we've got K, N is general, Q is general, K is 1, and M is Q. The lower bound is the for all Kakeya sets are at least this size. So this is the for all side. It's 2 to the minus, the best known is 2 to the minus n times q to the n. And the best construction, so there exists a Kakeya set in fq to the n of size 2 to the minus n plus 1 times q to the n minus, or plus q to the n minus 1. So those are the upper and lower bounds that differ by a factor of basically 2. And this has been the state of the art for probably 10 years now. I think that at least Zeev would be very interested if anybody managed to remove this factor of 2, but it's pretty close to being thoroughly understood. What is the upper bound construction? It's not so hard. I'll take a very short. I wasn't gonna say it. Basically, what you do, you look at this vectors of form, say A1. Let's call it alpha 1 to alpha n minus 1 beta 1. And we'll take, not beta 1. Beta is going to be any element of fq, and we require that A1 plus beta is either a square or not a square. I'm trying to remember which. Is a square. We take this union, the hyperplane. See. So, yeah. Union the hyperplane, say, so every point with a 0 in the last coordinate we take, and then we take coordinates where the sum, each coordinate summed with the last coordinate is a square. So this gives us we're choosing basically half of the choices for each of these coordinates, so it's got the right size. And if you choose a vector for the direction, then you can find the right y coordinate that has this contained in the set. So that's the construction. That was discovered by Dvir. The lower bound, the strongest lower bound, I'll just mention 2 papers. One is the problem was really solved by Dvir in 2008, and then this strongest lower bound is due to Dvir, Koparty, Saraf, and Sudan. And I think that was done in 2009. So actually more than 10 years this is the state of the art, but it's also quite good balance. So what I'm going to do is I will show you a proof of a lower bound, not this lower bound, but the original bound of Dvir, just to give an idea of what the polynomial method that's used is, and then we'll see, how close can we use this method to get to analyzing this the full general question. So let's say proof sketch. So let's, for contradiction, let S be a Kakeya set with the size of S less than 1 over n factorial times q to the n. So this is a weaker bound than what's over there. And also I'm not going to actually do the calculations. But if you work out the calculations in the sketch that I did, this is the bound that you would come up with. So it's basically, we have 3 steps to the proof. First of all, claim is there exists a non-zero degree v less than q polynomial f such that f of x is equal to 0 for all x and s. So we have some set of points in FQN. We're going to find the degree v polynomial that's less than q, non-zero, that vanishes on our set. Now, why is it that we can do this? It's just a linear algebra problem. The number of coefficients of a general q minus 1, degree q minus 1 polynomial and n variables is this. And so if this is less than, and each point, yeah, this is the wrong way. Each point in our set S imposes homogeneous linear constraints on the coefficients of the polynomial that we're choosing. So as long as the number of coefficients is greater than the number of constraints, there has to be a non-zero solution. Second step is that f vanishes, not vanishes, but f restricted to the lines of the Kakeya set is a zero polynomial. Let me explain what I mean by this. So for any pair of points v and h, we can define the polynomial p of v, or any pair of points v and u, we can define the polynomial p of v u in a single variable lambda to be f of u plus lambda v. So we're taking the line u plus lambda v and looking at the evaluations of f along that line, and that gives us a polynomial in a single variable p of pvu. And what we know from the definition of a Kakeya set is that in every direction, so for all v, there exists a u such that pvu is 0, because for all v there exists a u such that there's q zeros on a degree at most q minus 1 polynomial. A non-zero polynomial of degree q minus 1 can only have q minus 1 zeros, so just a factor theorem pretty much tells us that this particular polynomial is 0. And so this is the polynomial of f restricted to the line. And so for each direction there's some line that's 0 in that direction. The third step is we want to conclude we conclude that f is 0 as a polynomial here. The way that we do this is, it's actually not too relevant to my talk, so I'm just going to hand wave over it. But I can give more details if you want. We're going to look at the highest, we'll look at the degree d part of these two. So this is a homogeneous, we're going to look at the degree d part of p of vu and of f. This is some homogeneous degree d polynomial. And if you just what is, say, let's say this is the degree d part of lambda. It's pretty easy to see that this is equal to, it only depends here on v, right? Yeah, this is just, you can see that by writing it out, and then, but we know that the coefficient here is 0, so this is evaluating to 0, so now we have a degree d polynomial that vanishes at every point in the field. So now it has to be now f has to be a 0 polynomial, 0 as a polynomial. But that's a contradiction because we initially found f to be a non-zero polynomial. So that's the whole proof. Okay. Oh, I got what? Get some space here. It's pretty good. It's just low. Okay. Okay. Next observation is actually this proof. That proves something more general, because this this choice of q here didn't have anything to do with the proof. I could just stick an m in here. I can find, as long as I make s to be small enough, I can find a degree d less than m polynomial that vanishes on the set, and everything else goes through. So this exact, and in fact, the same proof that gives us better constant also works. So we can say that k of n. This is going to go too low. I got to erase some. I can switch the boards. That's what I'll do. That's good. All right. So we know k and q on m is at least 2 to the minus n times m to the n. Now there's actually a matching upper bound due to Wusheng-Zhang in a higher dimension. Well, it's due to Wolf in the plane. In the same paper as before, and also Wusheng-Zhang generalized it in 2014 to higher dimensions, and this is, well, if Q is a square and your field has, if you have subfields, then this bound is up to the constant factor is tight. So we're going to say, if you're in a square field, then there's some constant that depends on n only times n to the n. But that's not really the end of the story for this question. Wusheng also showed that the presence of a subfield is really necessary for this to be tight. This is not M, sorry. This is P. Yeah. So here so if P is prime, then we can get a better lower bound. for exactly this midpoint of p, square root of p points on each line, in a line on each direction. So this is at least some constant depending on n times p to the n over 2. That's the same bound as this up to the constant plus something positive depending on n. So if we fix n and take p very large, then there's no way to get a Furstenberg set of this size. So I should say that this is called a Furstenberg set. We've got k is equal to 1, m is at most q to the k, and positive. So there's something much more complicated going on for Furstenberg sets that didn't really occur for Kakeya sets. And this is, there's still, improving any of these bounds is still open. For this one, p is prime. This one is just the field has to be square, so it has to have a square root size subfield and then the construction. P can be a power of a prime. Yeah. Yeah. Here only the p has to be a prime. So for so now let's look at k-plane Kakeya sets. The requirement is that in every direction, for every k-dimensional subspace, there's a translate of it that's contained in the set. So we'll say k-plane here's k is general, well, k is at most n, I guess, and m is q to the k. This proof outline that I gave before still works. If you have a set, you take a polynomial, it vanishes at q to the k points on every k-plane, then in this case, you can say something about the degree of this polynomial. We have, but in this case, you can't really generalize it to arbitrary n. So if we have some, here's a k-plane, and we have some points, we know that we've got m points in this k-plane. But what we can say about the degree of a polynomial that contains m points is that a degree d polynomial contains at most d times q to the k minus 1 points in a k-plane. So if m is greater than q to the k minus 1, we can say something. If m is smaller than q to the k minus 1, then the fact that you have a polynomial that vanishes on a large number of points in your k-plane says nothing at all about that polynomial. So this same basic proof, zeros, contains, vanishes on. How about vanishes on? Yeah, the zero set of a polynomial contains at most so many points. Thank you. And of course, this can't be improved because that's what you get if you take just a product of linear factors. So this was pushed through by Ellenberg Oberlin and Tao in I think 2010, and improved by Lev, Koparty, Zeev, and Sudan, maybe 2012. I'm not going to show exactly what the bounds are, but this third step that I didn't really say very much about works much better when you have when your polynomial is vanishing on k-planes. So here we get that both the upper and lower bounds are for large fields and for k at least 2. You get almost everything. Here, this little one function is, the function depends only on n and k, so q is the asymptotic parameter. So if you take q to be very large, you get almost all of the points in any k-plane Kakeya set. But this proof is useless because the proof is useless for the general case just because the second step fails. So let me So Jordan Ellenberg and Daniel Erman in 2015 made some progress on the problem. What they showed is that every KM Furstenberg set contains at least some constant depending on n times n to the n over k points. In fact, they considered a much more general problem for schemes. And for the question that they were studying, so they're looking at schemes, and they were looking at a problem that they defined for zero-dimensional schemes, and the point sets falls out as a very special case for reduced schemes. And for the general problem, this m to the n over k is the right bound. You can't improve it. For the original question having to do with point sets, it turns out that this is very far from being the correct bound. And so kind of the story behind this work is that Zeev and Manik and I wanted to understand this proof. Found it quite hard. We worked through it, simplified it, improved some parts of it. So, for example, this constant in their work is something like 1 over n to the order n log n over k. What we showed is the constant is 1 over one over 16 to the n log n over k. And this, although the 16 isn't typed here, the kind of functional form is constant to the n log n over k times m to the n over k. That's basic. That is the type bound for this more general question. But basically, we rewrote the proof in more elementary language and improved a few of the lemmas. But it's this paper, which is called Explaining and Improving the Ellenberg and Erman Proof, is just rehashing their proof without using the language schemes. But while we were just about finished writing this paper up, we came up with a much simpler proof for the original, simpler proofs for the original problem and gave much stronger results. And that's what I want to spend the remainder of the time talking about. So I'm going to erase everything except for what? Except for the definition of a Furstenberg set. We have two theorems. The first is a completely general lower bound on the size of a KM Furstenberg set. So this constant is too strong, is already too strong to work for the more general question having to do with schemes. However, in the case that n is large, we get a much stronger bound. So if n is at least 2 to the n plus 7 minus k times q, then the lower bound takes it from n times q to the n minus k times 1 minus little of 1. Here, the way to think about this little o is that the function is depends on n and k. We're saying m is a function of q, and q is the large asymptotic parameter. So if you fix m to be a function of q, so like maybe q to the k over 2, and fix n and k to be constants and take q large, that's when you get the little o of 1. So this bound is tight, and it's for a very trivial reason. I've got a question. Can anybody think of an example of m times q to the n minus k points that is an n minus mk Furstenberg set? So.
You take something like first coordinate only on the left.
Yeah, that works. So let's take your favorite set of m times q to the n minus k points. Now choose your favorite direction and look at all the k flats in that direction. There's q to the n minus k of them. So by an averaging argument, one of them has to have n points. Okay. So, let me show you the, well, I'll give a sketch of the proofs. Please use two different, oh, no, before I do that, first notice that this bound on M, it tells us that Q has to be large. This bound really says nothing at all for the small field case. I mean, Q has to be something like 2 to the n over k. So we really need, in high dimensions, we really need, when k is relatively small and n is relatively large, we really need the field size to be large in order for this bound to be in effect. The other thing is that we don't have applications for this yet, but if there were applications in computer science, we would primarily be interested in the case of a fixed, where the field size is fixed and the dimension is large. So we'd still be sort of stuck with the weaker bound. So there's an interesting open problem is what's the truth for small fields? We really have no non-trivial constructions for the case that, say, the field size is fixed. In every direction, there's a k-flat. K is relatively small. There's a k-flat that contains, say, q to the k over 2 points, something along those lines. And I think that it's a very interesting range of parameters. Really, this is the range of parameters that the people coming from analysis were mainly interested in. They were thinking about Q as this field as being very large and the dimension is fixed. But for the computer scientists, it's more interesting the other way around when the dimension is large and the field size is fixed. So our results are much stronger in the case that the field is large and the dimension is fixed. So in order to give the proof of theorem 1, which I'm not going to give a proof, but I'll give a kind of hand wave over the ideas, I need to give a definition of, which probably many of you have seen, is min entropy. So let's let R be a random variable supported on FQN. I'm going to say that the min entropy of R is negative log. We're using base Q because it's just more convenient because we're dealing with powers of Q, so it's nice to take our log space Q. Of the maximum probability of any point being pulled. So there's some very easy bounds on this. We have the min entropy is always going to be bounded between n and 0. 0 is the support of R. If R is supported on a single point, then the maximum probability of pulling any point is 1, and the log of that is 0. On the other hand, if we have R is uniform, then every x is equal at 1 over q to the n, the log of that is n. Well, negative n, but then we take the negative. So that's the range. And in general, you can kind of think of the relative entropy. If you take how random is how close to being uniform is a random variable q to the n, well, if we normalize this to be between 0 and 1 just by dividing by n, that gives us a nice number that we can compare between dimensions. So kind of our real theorem that implies theorem 1 is what follows. So for all such random variables R, there exists an onto linear map phi from fqn to fqn minus k, such that the mid entropy of the kind of projection of R on fqn is at least, well, it's at least what the best you could hope for, minus a little bit. The best you could hope for is n minus k over n times the mid entropy of R. This is just because we're moving from a dimension n to a dimension n minus k. And then we lose something, which I have to look up, minus k log base q of 2. So the claim is that theorem 3 implies theorem 1. So let's let S be a K Furstenberg set. So let U sub S be the uniform distribution on S. So what does the fact that S is a Furstenberg set tell us? If we choose, it tells us that in every direction there's a k-plane that contains at least m points. So if we, for every onto linear map from fqn to fqn minus k, well, the points in our image correspond to k-planes in the pre-image. So there has to be always some point, the probability of which is you're going to hit it is going to be m divided by the size of S. So the Furstenberg property says that for all linear maps phi of the form that we're interested in, there exists an X in the image such that the probability of phi of U sub S being equal to X is at least m divided by Cardinality S. So now we can give an upper and lower bounds to So the mean entropy of phi of the uniform distribution on S, well, we know that it's at most log base Q of cardinality S over M. And we know that it's at least N minus K over N times what's the min entropy of the uniform distribution on S? That's going to be just log base Q of S minus K times log base Q of 2. And now you just do some arithmetic and you can get a lower bound on cardinality of S. So why is this a good reformulation? Why do we prefer this formulation to the one that we had previously? Well, the answer is that when you take a random variable and you take a onto linear map from one dimension to the one down, you get another random variable. So there's a hope. So what we do is by induction, we know how to handle the kind of the one step. This is polynomial method. Now we can just do an induction down. So I can draw a picture. Here's our original space. Here's our original set. Instead of handling the full drop in K, instead of going straight from F cubed N to F cubed N minus K, we'll just go down one dimension. So here's F cubed N minus 1. Here's some onto linear map. And here's the projection of our set. And this isn't any longer a uniform measure on a set, it's just something else. And so we can just keep on going. And eventually we get down to the target. And this is our projected set. And so the biggest problem is just handling the inductive step, and this can be done using the polynomial method, even though you can't go straight from this beginning to the end by the polynomial method. And so that's why we get exactly the same constants here as you get for the Kakeya bound, because we're using the same proof. So there's only 10 minutes left. I can't say very much about the other theorem. But there's a reason that maybe it's not so surprising that the Furstenberg or the K-plane versions of the sets are much larger than the line versions of the set. You look at how many two flats are there, say, in FQN versus how many lines are there in FQN? Well, there's a lot more. The closer that you get to the middle of this, the middle dimension, the more you have. Another point is that there are just more points on each K-flat. So this is a much, heuristically, the condition that we have here is much stronger when K is larger. So we ought to expect that the size of the set is bigger. But the problem is that there's really not so many, there's not so many K-flats in our set. We only have one in each direction. There's very standard methods that say that if you have a very large set of, say, lines in a vector space over FQ, that it's going to take up almost the entire space. This is just using expander mixing lemma, basically. So we'll look at, say, let's look at points. This is all points in FQN. And then let's say this is, let's say it's Q minus 1 flats in FQN. So maybe there's a lot more vertices on this side. but it's easy to analyze the eigenvalues of this graph. There's a bipartite graph where the left vertices correspond to points, the right vertices correspond to some subspace or some affine subspace, and we draw an edge if the point is contained in the subspace. So if we have let's say we have some set S over here, the size of which is alpha. Let's call this left vertices are P, right vertices are L, alpha times P. And we have some set T over here, the size of which is beta times the size of L. And alpha, if alpha and beta here are constants, then, well, they don't have to be constants, but it's really only useful when they're large. The number of edges between S and T divided by the number of edges in the graph minus the expected number if S and T were random is not too large, depending on how large is the second positive eigenvalue of this graph. So this times square root alpha beta. So if you can get into the happy situation where you're looking at a very large set of points and flats, and you know, then you win, basically. But the problem is that we don't have enough k-flats. So what we want to do is show that if instead of looking at the k-flats, we're going to look at the k-1 dimensional flats. So just for concreteness, let's imagine that k is 2. So we start out with a plane in each direction. What we're going to show is that if we look at the lines that are contained in each plane, and each line contains a large number of points, then the total number is actually a positive fraction. So we end up with a positive fraction of lines, each one having a very high degree here, and so the number of points that we had has to be large. But the question is, how do we move from having 2 flats in every direction to having lots of lines? And then we can use the Kakeya bound as a black box. So I'm not going to say more about the expanded part. What I'll show is how do you get a large set of lines from a set of planes in every direction. Does that make sense? Maybe. This will be a picture proof. So let's say we've got W1 to Wn. These are 2 flats in each direction. Save it. L sub I is the lines contained W sub I, and L is the union of the L sub I. So we're looking at lines that are we're only looking at lines that are completely contained in one of our 2 flats, not just the union of the 2 flats. And the claim is that the cardinality of L is at least 2 to the minus n plus 1 times the total number of lines. So we start out with a relatively small number of 2 flats, and now we're going to find that a constant fraction of all of the lines in the entire space are contained in those 2 flats. Constant being 2 to the minus n. So let's choose some vector v, arbitrary. Then we're going to say that u is a n-1 flat that does not contain v. And we'll look at a bunch of planes. We'll look at those planes that contain and translate to V. So we fix some vector, and we're only looking at the planes that contain and translate to V. So we look at let's say Wi. There exists some U with U plus W, U plus V in W. Now the claim is if you look at, certainly each Wi intersects U in a line, it turns out that the union of these lines is a Kakeya set. And every point in this n-1 dimensional flat corresponds to a line in the direction of V. So we know the density of a Kakeya set is positive. It's at least 1 over 2 to the minus n plus 1 because we're in an n-1 dimensional space. And since we started out with an arbitrary vector V, that's true in every direction, that we have to contain a positive fraction of the lines going in that direction. So then there's a little additional work. We kind of use this idea twice. First, in every plane, we show that almost all the lines have about the average number of points, so we throw away the lines that don't have very many points on them. And then we have a constant fraction collection of lines. Every line has a large number of points in our original set S, and that allows us to say that the set S has to be large. Just using this it's kind of averaging argument. Okay, that is the end of my talk.